Welcome to the fourth lesson of the seventh module, which is on deflection of beams part 4. In fact, in the last 3 lessons of this particular module, we have discussed how to evaluate the slope and deflection in beams for different loading situations, considering the differential equation of elastic curve, and also we have looked into the method of superposition, how to employ method of superposition in evaluating slope and deflection of beams, and subsequently we have looked into the theorems of moment area or moment area method to evaluate the slope and deflection in beams. Now, in this particular lesson we will be concentrating on the evaluation of slope and deflection of beams employing moment area method again, but in the previous examples we have looked into for the beams where the EI value or the flexural rigidity is uniform throughout the beam. Now, here we will be considering the beams where EI may not be uniform throughout the beam, there could be variable moment of inertia, or if there is a non-prismatic beam where it is varying continuously, then what will be the values of slope and deflection in such beams. Hence, it is expected that once this particular lesson is completed, one should be in a position to understand the use of moment area method in evaluating slope and deflection of non-prismatic beams or beams with variable moment of inertia. One should be in a position to evaluate slope and deflections in different types of beams for different loadings. The scope of this particular lesson includes the recapitulation of previous lesson, and we will be doing that through the question answer sessions. We will be answering the questions which were posed last time, and thereby we will recapitulate the previous lesson. Use of moment area method in evaluating slope and deflection in non-prismatic beams or beams with variable moment of inertia. Also, this lesson includes the examples for evaluation of slope and deflection in different types of beams for different loadings. Well, let us look into the answers of the questions which were posed last time. The first question is, what is the method of superposition? Now, if you remember, we said that in a particular beam, if we are interested to evaluate the slope and deflection for multiple loadings like the loadings shown over here, that this particular beam which is simply supported subjected to uniformly distributed load of intensity Q per unit length, and also it is subjected to concentrated loads P1, P2 and P3. Now, if we are interested to evaluate displacement or deflection of this particular beam at this point for these loadings, then we can employ any of the methods which we have learned. Let us say the usage of differential equation of elastic curve. We can use differential equation of elastic curve which says that EI d2i dx2 is the bending moment m, and we can employ that to evaluate the deflection at this particular point for general loading as shown. Also, we can evaluate the deflection of this particular point using this method of superposition, wherein we use individual loading. Instead of considering all the loadings acting on this particular beam, we consider the loads one by one and evaluate the deflection at this particular point for each individual load, and finally we sum them together to get the final deflection at this particular point. And it is expected that the results which we get in either case, that in the first case when we use the differential equation for elastic curve for the whole lot of loading and compute the deflection, and if we employ method of superposition by using differential equation or area moment theorem, and if we evaluate the deflection at that particular point for individual loading and sum them up, the results should be identical. And this is what method of superposition says, that for the linear response of the structures, and this is quite important, that when the response of the structures is linear, it means that the deflection which we compute is a linear function of the load, and then the effect of several loads acting simultaneously may be obtained by superposing the effects of the individual loads. And for this you will have to satisfy these two criteria. One is that it must, the material with which the beam is made up must obey the Hooke's law, and the deformations are sufficiently small, so that we can employ this superposition technique. So, this is what we call as superposition. Now, second question was, what is the use of moment area method? Now, we have seen that in the last lesson we have discussed about the moment area method, and consequently we have discussed the two theorems, moment area theorems. Now, they are useful in determining the slope or deflection of a beam at a specified location. Now, for using moment area method, as you have noticed that we need to employ the bending moment diagram of the particular beam for which we are interested to evaluate slope and deflection, and from bending moment diagram we arrive at the m by EI diagram, and that is what is of interest for employing moment area method, that we draw m by EI diagram from the bending moment diagram, and using this m by EI diagram we compute the value of slope and deflection in a beam at a particular location where we are interested in. And the last question given was, what is the value of end rotations in a simply supported beam subjected to concentrated load P at the center of the beam? In fact, we have discussed this example and we have solved it using differential equation of elastic curve as well as using moment area method. And as we have seen that when we compute the value of the rotation at the end, the value of the rotation comes as P L square by 16 EI. So, the value of the end slope whether at A or at end B, because this particular beam is symmetrical and is symmetrically loaded, hence these two magnitude wise both theta n and theta b are the same, which is P L square by 16 EI. And from the sign convention, as you know that from this axis it is rotating in a clockwise direction, from this axis it is rotating in an anticlockwise direction. So, for this matter it is negative, and according to our convention this is positive, and this is what is indicated over here. Theta b is equals to minus theta a, and magnitude wise it is P L square by 16 EI. So, those were the answers of the questions which we had posed last time, and as I have told you that in the 3 lessons of this particular module we have seen that how to compute the value of slope and deflection in a beam for a particular support conditions, and also for a particular type of loading how to compute the values using differential equation of elastic curve or moment area methods, or employing any of these using superposition method we can compute these values. Now, here in the previous examples whatever we have computed so far, you must have noticed that we have used the value of EI which we have defined as flexural rigidity, we have kept constant throughout the span of the beam. That means, the value of the moment of inertia is constant, or in other words the cross sectional parameters of the beam is not changed throughout the span of the beam. Now, the question is, if it is not constant, if EI is a variable parameter, then what happens, and that is what we are going to look into today. Now, in this case let us see that many times for economic reasons we use this I cross section of the beam, as you have seen that cross sectional area which is in the form of a I is useful because this the areas are massed away from the neutral axis, and as a result this particular section contributes more to the moment of inertia I. Now, as we have seen that if the beam is a simply supported one subjected to different kinds of loading, either concentrated load or distributed load, the maximum bending moment occurs at the center of the span, at the center of this particular beam. Now, to enhance the strength of the beam, many a times in the central region we add some additional material, so that the moment of inertia can be enhanced further. That means, on to top of these we can add some plate on either side, so that the moment of inertia of the cross section in this particular region can be enhanced. Now, as you have seen that the bending stress sigma is equals to m y by I. Now, if we increase the value of I, then the value of sigma comes down, and thereby this will be more effective in carrying the stress if we can increase the moment of inertia in the central region. Now, if we do that, then this particular beam becomes a section, a different section, it becomes the variable cross sectional area. That means, at this particular location this may be I, in this particular location this may be twice I or some fraction of values of I. So, thereby you have different values of moment of inertia in these regions, and as a result if we like to employ the differential equation, which is E I d2y dx2 is equals to moment, then we cannot employ the uniform expression for all the regions. We will have to write down this differential equation for different regions and we can compute it. Now, in this particular case it becomes rather simpler, but for a case where you have a beam of this particular form, where the section or the beam is a non-prismatic one, that means any section you take, the cross sectional parameter is changing always, and thereby the value of the moment of inertia I is changing, and its function of x along the length of the span. Now, since this I is in the denominator, as you have seen that when we compute that m by E I diagram. Now, this becomes a little complex when we try to evaluate the slope and deflection, but still we can use the moment area method in evaluating the deflection and the slope of such beams by making a little simplification. Now, instead of considering this non-prismatic one, for a particular length of the beam we can make it a prismatic one, and thereby we can think of that this particular section is composed of several prismatic part, and for this particular region we can write down the differential equation, or we can evaluate m by E I diagram for this beam segment wise, and we can compute the value of slope and deflection. Now, in the process the slope and deflection which we evaluate for the entire beam, now though it is not going to be exactly the same if we consider the moment of inertia which is a function of x, but nevertheless we can accept this solution for with reasonable accuracy for using in the design practice. So, we can employ this kind of technique for evaluating the slope and deflection in a beam, and that is what we will be looking into while solving the examples on such, and we will be demonstrating the effects of this using some examples, and we will see that how do we compute the slope and deflection in beams which are non uniform, that means the moment of inertia is not uniform throughout the span of the beam, or if the sections are non prismatic. Well, let us look into the example problem which I had given to you last time for evaluating the slope and the deflection. So, deflection at the mid span and slope at the supports for the loading indicated over here, and you will have to use moment area method to evaluate the slope and deflection. Now, this particular load is acting at the center of the beam. Now, to employ the moment area method, as you know, first we should know the bending moment diagram, and the each ordinate of the bending moment diagram, if it is divided by the flexural rigidity E I, the resulting diagram which we get, that becomes m by E I diagram. Now, to obtain the bending moment diagram for this beam, what we need to do is as a first step is the evaluation of the reactive forces. So, let us call this end as A and this end as B. So, the reactive forces that will be acting at the hinge is R A and H A, and at support B is R B, as you have seen earlier, and since there are no horizontal force, H A will be equals to 0. So, we are left with only R A and R B, and if we compute the values of R A and R B will be equals to the half this concentrated load which is acting, which is P by 2, and thereby if we take any section over here, then the moment will be equals to R A times x, and at L by 2 it will be P L by 4, and again at this point and these two support points it will be 0. So, if we plot the bending moment diagram, the bending moment diagram looks like this, that at the two ends the value of the bending moment is 0 and at the center we have the value of the bending moment as PL by 4, and when we divide this by EI, this becomes PL by 4 EI, and truly speaking now this is M by EI diagram and not the bending moment diagram alone. So, this is the bending moment diagram divided by the flexural rigidity EI of each ordinate, and thereby this is M by EI diagram. Now, we like to compute the value of the deflection at the center, and being symmetrical, this is the maximum deflection, that is what we are going to obtain at this particular point, and also we need to find out the slope of this beam. Let us call this as theta A. Now, we employ the second moment area theorem to evaluate the tangential deviation of point B with respect to point A. Now, as you know, the second moment area theorem states that the tangential deviation of any point on the elastic curve, in this particular case let us say this is B, with reference to the tangent drawn on any other point on the elastic curve, which is A here, which is, if we draw the tangent from A and this is the tangential deviation which we call as TBA, is equals to the moment of the M by EI diagram taken about the first point. So, if we take the moment of this M by EI diagram with respect to point B, we get this tangential deviation of point B with reference to the tangent drawn at point A. So, let us evaluate this value TBA. So, TBA, now here this whole triangle we can divide into two parts. One is this one, this is this is first one and this is second one. Now, for the first one, if we take the moment of this triangle with respect to point B, this is half and this distance is L by 2. So, half L by 2 into the ordinate is PL by 4 EI, and the CG of this particular part of the triangle, which is this distance, which is 1/3 of L by 2, and this is what has been taken over here, 1/3 of L by 2 plus this distance L by 2. So, that is the moment of this particular part of the triangle. Then if we take the moment of this triangular part, half into L by 2 into again ordinate is PL by 4 EI. Now, this distance, the CG distance from this end is 2/3 of L by 2, and this is what is written over here, 2/3 of L by 2, and if we compute this, this becomes PL cube by 16 EI. So, this particular length, that means the deviation of this point B on the elastic curve with respect to the tangent drawn at point A, this distance is TBA, which is equals to PL cube by 16 EI. Also, if you look into this particular diagram, say AB, let us call this point as D, from this triangular part ABD, we can write that distance BD is equals to the slope theta A multiplied by length. So, BD is equals to the slope theta A multiplied by the length, and BD, which is TBA, as we have seen as PL cube by 16 EI, this is equals to theta A multiplied by length L. So, theta A is nothing but equals to PL square by 16 EI, and this is what is indicated over here. So, value of theta A is equals to PL square by 16 EI, and this we have seen earlier using differential equation of elastic curve. Now, what we are interested in is to evaluate the deflection of point C, which is going to be the maximum deflection in this particular case, because this is a symmetrical beam and acting the load also is symmetrical with respect to the beam. Then if we like to compute the value of the deflection, which is from here to here, this is the value of the deflection, let us call that as delta. Now, if you like to compute delta, now how do we do that? Now, at this particular point, again if we try to compute the value of the tangential deviation of this particular point with reference to the tangent drawn at A, we can evaluate this particular distance, and this we call as TCA. the tangential deviation of point C with respect to the tangent drawn at A, and the whole distance from this center to this particular point, we can get this length as this length is equals to theta A multiplied by L by 2. So, from the whole distance, if we subtract this particular part, we get the value of the delta. So, let us compute then the value of the delta, which is now the TCA value, the tangential deviation of point C with respect to the tangent drawn at A, is equals to the area or the moment of the M by EI diagram between A and C taken about C. So, the area of the M by EI diagram between A and C is half L by 2 times PL by 4 EI, and if we take the moment of this particular area with respect to point C, it is distance is 1/3 of L by 2, and this gives us a value of PL cube by 96 EI. So, the value of delta, as I said, is equals to theta A multiplied by L by 2 minus TCA. Now, theta A, as we have seen, is equals to PL square by 16 EI. So, this is PL cube by 32 EI minus PL cube by 96 EI. So, this gives us a value of, this is PL cube by 32 EI minus PL cube by 96 EI. So, if we compute this, this is going to be equals to PL cube by 48 EI, and we have seen earlier that the maximum deflection which we get in a beam which is simply supported and subjected to a concentrated load at the center gives us the value of PL cube by 48 EI. Also, please note over here that in this particular beam, this being a symmetrical beam with symmetrical loading, now the elastic curve which we get also is symmetrical, and as we have seen earlier that the values of the rotations which we get at the end, they are the same. Now, what will be the value of rotation over here? As you have seen that theta A equals to PL square by 16 EI. Now, if we draw a tangent at this particular point, at the center point of this beam, that becomes, now if we draw the tangent at this particular point of the elastic curve, the tangent at this point is horizontal, and as we had said that this gives us the maximum value of the displacement or the deflection where the tangent to the elastic curve is horizontal. Now, if we take the tangent at this particular point, at the central point, and draw it up to this, and if we consider these 2 points, we can say that the tangential deviation of point A with respect to the tangent drawn at point C, which is this, equals to this distance, which we can call as say TAC. That means tangential deviation of point A with reference to the tangent drawn at point C. Now, this distance is nothing but equals to this particular distance, which is the deflection. Hence, we can compute the value of the maximum deflection from this particular part of the M by EI diagram as well. Now, what we can do is we can find out the moment of this particular part of the bending moment diagram, which is between A and C, and taking the moment of the EI diagram about A will give us the value of the deflection. Now, if we do that, then moment of this particular diagram is half the area is L by 2 times PL by 4 EI. So, this is the area multiplied by the distance of the CG from this end, which is 2/3 of L by 2. So, 2/3 of L by 2. Now, if we do that, then we have 1648. So, this gives us PL cube by 48 EI. Hence, we get the value of the delta by computing this part of the bending moment M by EI diagram. We take this part of the M by EI diagram, take the moment of this with respect to A, and we get the tangential deviation of point A with reference to the tangent drawn at C, and that is nothing but equals to the deflection of this particular beam. So, in a simply supported beam, we can compute the value of the maximum deflection either in the way we have done first, that means we compute the tangential deviation of the support B with reference to the tangent drawn at A, and thereby first we compute the value of slope, and then at the center we compute the value of the deflection, or else in a simpler form we can take half the area of the m by e I diagram, take the moment with respect to point A and compute the value of the deflection, and you will get the identical result. So, you can apply this technique as well for evaluating the deflection. Well, now let us consider an example where the moment of inertia is not constant throughout the beam. Instead, we have variable moment of inertia. Over the part AB, we have the moment of inertia as 2y, and over the part BC, the moment of inertia is I. Now, in this beam, which is a cantilever, is fixed at one end and the free at the other, is subjected to a concentrated load at the tip, and we will have to compute the value of the deflection at the of the free end, and we need to use the moment area method. Now, if we do that, the first step will be to evaluate the bending moment of this particular beam. Now, if we consider, let us say, first uniform I, thereby we have the beam subjected to the concentrated load here P over the length L, and if we compute the reactive forces, that means removing this, if we replace these with the reactive values, we have vertical force, horizontal force and the moment, and we can compute the value of the, since we are interested in the bending moment diagram, we compute the value of the moment. So, value of the moment is equals to, if we call this as m, m is equals to minus p times L. So, at this point it is P L. Now, if you compute at any point, it is p times x. So, it is varying linearly from 0 to the maximum value, which is p times L. So, let us look into the bending moment diagram of this, and then we go for the m by e I diagram. So, this is the bending moment diagram, that means 0 bending moment over here, and at this point we have the maximum value of the bending moment, which is equals to P L. So, this external one shows the bending moment diagram, which is varying from 0 to linearly from 0 to P L. Now, when we like to employ the area moment theorem, what we are interested in is to evaluate the m by e I diagram, and as we know that m by e I diagram is nothing but the bending moment diagram divided by the e I value at each ordinate, and that gives us the m by e I diagram. Now, if you look into this particular part, that B to C, the value of the bending moment of inertia is I. Hence, if we divide each ordinate of the bending moment diagram of this particular part, at this particular point the bending moment is equals to, the value is P L by 2. Now, if we divide this by the E I value, then the ordinate of the m by e I diagram at this particular point becomes P L by twice I, twice E I. Now, since at this particular point there is a transition from I to 2I, so immediately next to this section the moment of inertia is 2I. So, the change from P L by 2 E I to, it will be changing to P L by 4 E I, because this is bending moment is P L by 2, that divided by 2I. So, this is going to be equals to P L by 4 E I. So, this is the value over here. So, from P L by 2 E I it goes to P L by 4 E I, and then again at this particular point the bending moment is P times L, that divided by twice I, that means this is going to be equals to P L divided by 2 E I. So, at this point again the m by e I value is P L by 2 E I. So, from P L by 4 E I it goes to P L by 2 E I and varies linearly. So, in effect this is going to be the m by e I diagram in this particular case. So, the m by e I diagram is something like this. Now, we will have to employ this m by e I diagram to compute the value of the slope and the deflection. Now, for computing the deflection or the slope, what we need? Now, we need to use the moment area method, and for using moment area method we will have to employ the moment area theorems, and as you know that for employing moment area theorems we will have to deal with the m by e I diagram. And the second of the moment area theorem states that the tangential deviation of any point on the elastic curve with reference to another point on the elastic curve, or you draw the tangent at that particular point, gives you the deviation is the that is equivalent to the moment of the m by ei diagram between those 2 points taken about the former point. So, if we do that, that means on the elastic curve it is expected that the elastic curve is moving like this. Now, if we choose 2 points, a point here and a point here, and if we draw the tangent at point A, which is a horizontal, because here the slope is 0, dy dx is 0. Now, the tangential deviation of this particular point C with reference to A is this value, which we have said as TCA. So, tangential deviation of point C with reference to the tangent drawn at point A is equivalent to the moment of the m by ei diagram between A and C taken about C. So, if we take the moment of m by ei diagram between A and C about C, then what do we get? Now, let us look into this expression for evaluating this TCA. So, TCA is equals to, now this m by ei diagram, which is of this particular shape, we divide into 3 parts. One is this particular triangle, and then thereby we are left with this trapezoidal area, and this trapezoidal area we can divide into 2 parts. One is this rectangular part with ordinate PL by 4 ei, and then this is the triangular part which is having PL by 4 ei as the ordinate. So, if we compute, or if we take the moment of all these 3 areas with reference to point C, then let us see what we get. Now, for this particular part, for this triangular area, let us call this as area 1, which is half PL by 2 ei is the ordinate, L by 2 is the length, times 2/3 L by 2 is the distance of the CG from here. This is 2/3 of L by 2. So, 2/3 of L by 2 is taken over here. So, that is the moment of this particular area with reference to point C. Now, if we take this rectangular area, now the ordinate here is PL by 4 ei over the length L by 2. So, PL by 4 ei multiplied by L by 2 is the area, and the CG distance here is from here to here is L by 4 and plus L by 2. So, L by 2 plus L by 4, plus if we take this triangular area, which is half into L by 2 times PL by 4 ei. This is PL by 2 ei and this is PL by 4 ei, which we have taken constant. So, balance is PL by 4 ei. So, half into L by 2 into PL by 4 ei, and the CG distance from this particular end is 2/3 of L by 2 plus L by 2. This distance is L by 2. So, L by 2 plus 2/3 of L by 2. Now, if we add these 3 parts together, the first part gives PL cube by 24 ei, second one gives you PL cube by 32 ei, and the third part gives you 5 PL cube by 96 ei, and if you sum them together, finally you get the value as 3 PL cube by 16 ei. So, this is the value of TCA is nothing but equals to the deflection of this elastic curve over here, that is what is the delta. So, delta is equals to 3 PL cube by 16 ei. And also, if we like to compute the value of the slope, if we take the tangent at this particular point, and here since the tangent is horizontal, so this will give us the value of the slope, which is equals to theta c, and this theta c is nothing but the area between A and C, area of the m by ei diagram between A and C, and that is as per the first moment area theorem, that the slope, the difference in slope between 2 points is equals to the area of the m by ei diagram between those 2 points. So, here the difference in slope between these 2 points is theta c, and we will have to take the area of the m by ei diagram between these 2 points. And if we take that, that means the first part of it, if we take the all the areas and sum them together, then we get the values, and that will give you here if we take this as PL square by 8 ei from the first part, plus from here is PL square by 8 ei again, that is the area of the rectangular part, and for the other triangular part is PL square by 16 ei. So, these are the 3 areas. If we sum them up, we have this as say 16 ei and 2 to 4 5 PL square by 16 ei. So, this is the value of theta at C. So, theta c is equals to 5 p l square by 16 e I, and the value of the delta is equals to 3 p l cube by 16 e I. So, as you can see that we can compute the value of the deflection delta and the slope at the free end theta c, even if the moment of inertia is variable using moment area method. Now, that is what I was trying to explain to you, that even if the beam is non-prismatic, we can make it, we can approximate in a segmental prismatic form, and we can employ moment area method to evaluate the slope and deflection in the beam, and that is going to give you a quite close value to the exact one, and we can employ that for a quick reference instead of going into very rigorous analysis. Now, if we compare these values, in fact, we have seen that if you have a beam which is having a constant flexural rigidity, or the moment of inertia if it is constant right through, we have seen what is the value of the deflection, what is the value of the slope for a cantilever beam. That means, if you have a cantilever beam which is subjected to a concentrated load at the tip, we have seen that the maximum value of the deflection comes as p l cube by 3 e I, and the slope as p l square by 2 e I. Now, at this stage we have seen that what is the value of the slope and the deflection. Now, let us make a comparison of these values to get an idea that what physically really we get a change because of this non-uniform moment of inertia. Now, you see that when you have uniform moment of inertia value I throughout, the value of the deflection was p l cube by 3 e I, which is 0.33 times p l cube by e I. Now, at this stage we have seen when we have variable moment of inertia, where over the half the length you have twice I, and for the rest of the half you had moment of inertia as I. That means, when you have this variable moment of inertia over the section, then the value of the deflection at the tip comes as 0.1875 p l cube by e I. So, you see that the value changes drastically from 0.33 to 0.1875. The change is of the order of around 43 to 44%. Now, if instead of making 50% as twice the moment of inertia, if we would have made that the whole beam is of having moment of inertia of value 2 I, that means we provide a larger section throughout the length of the beam, then what happens, the value of the deflection which we get is 0.17 p l cube by e I, which is half of this value when you have I. Now, if you notice over here, the change from this where we have variable moment of inertia over the half of the length to where we have the full length as twice I, the difference is not much. Now, also if you look into the value of the slope, in the uniform case we get 0.5 p l square by e I. For when we have constant 2 I, we get half of that 0.25. When we have 50% as 2 I, we get 0.3125. That means, from 0.5 it gets reduced to 0.3125. 0.3125 to 0.25, the reduction is not to that extent. Now, the idea is, if you look into physically, that either you can have a beam with uniform cross section having moment of inertia as I, or if you like to reduce the value of the deflection, we increase the value of the moment of inertia to 2 I throughout the entire span of the beam, and thereby the deflection value will be half that when it was with I. Now, instead of that, if we provide the larger moment of inertia over the area where you have larger value of the moment, as you have seen in the cantilever beam, the moment values is highest at the support point. So, towards the support point, from the mid span towards the support point, where we have increased the value of the moment of inertia twice than for the first half, we see that the value of the deflection we could reduce to a great extent, and in the process, in fact, we have economized on the usage of the material as well, since we have used 2 I only on the 50% of the length of the beam. Naturally, we have not used the material over the entire length of the beam, thereby we could make some economy on the selection of the section, and so we could make a trade off between the reduction in the deflection and less usage of the material as well between the two extreme cases. So, many times we employ this particular situation in the design, so that we can reduce the value of the deflection, at the same time we can economize on the sections which we use. Well, let us look into another example of variable moment of inertia when the beam is a simply supported one and is subjected to a concentrated load at the center. Now, as you have noticed that for this we get the bending moment diagram where the maximum value of the bending moment is at the center, which is in this particular form, and thereby in the central region if we have the moment of inertia of the section, here this part is I, this part is I and this part is twice I, as it is stated in this particular example, that determine the deflection at the center of the beam and slopes at the ends for the bending for the loading shown over here, and moment of inertia for AB and CD is I and for BC is 2I. Now, if we use moment area method for evaluating the slopes and deflection here, naturally first thing is that we will have to draw the bending moment diagram, and as you know, as a first step for drawing bending moment diagram, you evaluate the reactive values RA and RB, and for this case as you have seen, RA and RB will be equals to P by 2, and if you compute the value of bending moment at any section over here, you will have RA times X. So, at different points you can compute the value of the bending moment, which is linearly varying. Now, let us look into the bending moment diagram for this particular beam, which is of this particular form, which is shown over here. Now, here as you can see that the maximum value of the bending moment is PL by 4 at the center, which is P by 2 times L by 2, and at this point the value of the bending moment is P by 2 times L by 4, which is PL by 8, and so is at this point as PL by 8. Now, what we need to do is that we need to draw the M by EI diagram, and for drawing M by EI diagram we divide the ordinates of the bending moment diagram by respective EI values, and as you can see over here that for these two parts you have one EI value, for this part BC you have another EI values. So, over here this is flexural rigidity is EI, for this flexural rigidity is EI, and for this flexural rigidity is 2EI. So, when we divide by these magnitudes EI and 2EI, at this point we get PL by 8EI as this ordinate. Now, at immediately next to this particular point, particular section, we have change from I to 2I, and thereby there is a change in the M by EI value over here, which is going to be equals to PL by 16EI, and at this point again it is PL by 4 is the bending moment divided by twice I. So, this is PL by 8I, and here also it is PL by 8EI. So, these three ordinates they are all identical, which is PL by 8EI, and at these 2 points where there is a changeover from I to 2I, we have the values of the ordinates here as PL by 16EI. Now, so the M by EI diagram as we can see here is like this. It comes over here, changes over here, then goes like this, goes over here, changes here, and then comes like this. So, this is the M by EI diagram for the beam between A and D. Now, what we need to do is that we need to compute the value of the bending moment delta at the center, and we need to compute the value of the slope. Now, if we compute the value of the delta, now as we have done earlier, as I was stating you that at this point if we draw the tangent to the deflection curve, and since this is symmetrical, it is expected that deflection will be maximum here and the tangent to the elastic curve is going to be horizontal, and thereby the tangential deviation of point A with reference to the point, if we call this as say E, with reference to E. So, this is the tangential deviation, which is T A E, and that is nothing but equals to the moment of the M by EI diagram between A and E taken about point A. Now, this M by EI diagram which we have drawn, we can divide it into 3 segments. One is this triangular part, then we have this trapezoidal part, and this trapezoidal part we can divide into 2 areas. One is the rectangular part, another one is the triangular part, and if we take the moment of this particular half with reference to point A, then what we get? we have for the first part half into L by 4 is the length. Now, PL by 8 EI is the ordinate and the distance 2/3 of L by 4 is the moment of this area with reference to point A. Then for this rectangular part we have PL by 16 EI as the ordinate, we have L by 4 as the length, that is the area, and then the moment of this particular area with reference to point A, which is equals to L by 4 plus half of L by 4, which is L by 8. So, this is the moment of this rectangular area with reference to point A. And thirdly, we have this triangular area which is half times L by 4 is the length, PL by 16 EI, this is PL by 8 EI is the total ordinate minus PL by 16 EI. So, balance is PL by 16 EI, and the moment of this CG from moment of this particular area with reference to this distance is L by 4 plus 2/3 of L by 4. Now, if we evaluate these individual moments of individual areas, we get this as PL cube by 384 EI, 3 PL cube by 512 EI, 5 PL cube by 1536 EI, and if you combine them it comes as 3 PL cube by 256 EI. So, this is the value of the deflection when centrally you have the moment of inertia as twice that of the end part of it. So, in the two end zone we had the moment of inertia as I, and in the central zone we had the moment of inertia as twice I. So, we have added additional material at the central part of the beam to increase the moment of inertia value, and thereby we are reducing the value of the bending stress, because sigma is equals to my by I. By enhancing I, we are reducing the bending stress at that region, and consequently we are reducing the value of the deflection as well. Now, that is what we see over here. The value of delta comes as 3 PL cube by 256 EI. Also, if we compute the value of the slope at this particular end, now when we draw the tangent to this elastic curve at this point and when we draw the tangent to the elastic curve at this point, since this is 0, so this is the equals to the slope theta A. Hence, we can take the area between these 2 points to evaluate the value of theta A, and consequently we get the value of theta A as, if we add up this area, now area is equals to half L by 4 times PL by 8 EI, which is PL square by 64 EI, plus we have for this part of the area which is PL square by 64 EI again. So, PL square by 64 EI plus we have for this particular part which is PL square by 128 EI, and if we add them together we have 128 EI and this is 224. So, 5 PL square by 128. So, this is the value of the slope which we have, and this being symmetrical, the value of theta A and theta B magnitude wise it will be the this value 5 PL square by 128 EI. Now, if we again make a comparison of the values which we have seen earlier. Now, in a simply supported beam where the value of the moment of inertia is uniform right through, where the flexural rigidity you have uniform, then we have seen the value of the maximum deflection is PL cube by 48 EI and the values of the slope as PL square by 16 EI. Consequently, if we make the value of I as 2I right through, that means if we have uniform flexural rigidity, but instead of EI now it is twice EI, that means we are adding more material to it, then naturally the values of the deflection will be half of the previous one, and so will be the slopes. Now, if we make the combination of these two which we have seen right now, and we have seen the maximum value of the deflection which is 3 PL cube by 256 EI, and consequently we have looked into the value of the slopes. Now, if you make a comparison, you see that the value of the deflection which you get for constant I is 0.0208 PL cube by EI, and in contrast when you have this variable moment of inertia you have a value of 0.117, a drastic reduction from this to this, and if you have uniform twice I, then your value is 0.0104. In fact, from these to this the reduction is not to that extent, and so is in case of slope. You see here we get 0.0625 For the variable moment of inertia we get 0.0391, and when it is becoming twice EI we are getting 0.0313. Hence, the reduction again from here to here is not that much to the extent as we achieve over here. So, by making variable moment of inertia, in fact we can achieve economy both in terms of the deflection or the stresses, and as well as the economization on the usage of the material, and thereby where we have the larger value of the bending moment, if we go for a larger cross sectional area, thereby you can have less stress, you can have less deflection, you can have less value of the rotations at the end. Well, we have another example where it is a cantilever beam subjected to uniformly distributed load, and the flexural rigidity EI is constant for the beam. You will have to use moment area method. Now, here of course, you will get a diagram which is not a linear one, and we have seen the diagrams which are linear one, and thereby it was easier to adopt the moment area method. Now, for this, as you know that when you compute the value of the slope theta b is the area between m by EI diagram, which is in fact 1/3 for this parabolic variation, the 1/3 of the rectangular area, which is 1/3, and as you know the magnitude of the maximum bending moment is QL square by 2 divided by EI will be QL square by twice EI. So, it is 1/3 into QL square by twice EI over the length L. So, this is equals to QL cube by 6 EI, and the value of the delta, which is the tangential deviation of point B with reference to the tangent drawn at A, is nothing but equals to the value of the delta or the deflection of this particular beam. That should be equals to the moment of the m by EI diagram between these 2 points. So, this is the m by EI diagram, and if we take the moment of this diagram with reference to point B, then we get the value of the delta, which is area is 1/3 into QL square by 2 EI times L is the area, and moment the CG distance from here is 3L by 4. So, if we multiply that we get QL 4 by 8 EI, which we have seen earlier as well. So, by employing moment area method to this, we can compute the value of the slope and the deflection of this particular beam. Well, you have another example over here. You got to compute the value of the tip deflection and slope of the free end for the loading shown over here. Here the loading is a triangularly varying load with a 0 intensity over here and maximum intensity Q0 at this particular end. The flexural rigidity EI is constant throughout the beam. You got to compute the value of the tip deflection and slope at the free end. Now, here we can employ the differential equation of the elastic curve. Now, at any section from this support at a distance of x, if we say the value of loading is q, since it is linearly varying, is equals to, in terms of this maximum value q0 will be L minus x by L times q0, and as we know that EI d4 by dx4 is equals to minus q, which is equals to minus q0 by L at L minus x over here, and if we integrate this we have EI d3 by dx3 is equals to q0 by twice L minus x square plus c1. Now, at x equals to L, the shear force is equals to 0. So, d3 by dx3 equals to 0 at x equals to L, that gives us c1 equals to 0. Hence, EI d3 by dx3 is equals to this q0 by twice L minus x square. Now, if we integrate this again, we have EI d2 by dx2 as equals to minus q0 by twice L minus x cube by 3, which is minus q0 by 6 L minus x cube, plus of course, we will have the constant c2. Now, at x equals to L, again the bending moment is 0. So, that gives us that c2 also is equals to 0. So, this is the expression for the bending moment. Now, if we integrate this further, we have EI dy dx as equals to q0 by 6 L into L minus x to the power 4 by 4 plus c3, and consequently EI is equals to this, where we have unknown constant c3 and c4. Now, at x equals to 0, y is 0, these are the boundary conditions, and at x equal to 0, dy dx also is 0, and if we substitute that, we get the value of c3 and c4 as this. Now, if we substitute the value of c3 and c4, we get the expression for y as this, that q0 by 120 EIL a 12 minus x to the power 5 plus 5 L to the power 4 x minus L to the power 5 and dy dx as this, and if you substitute x as equals to L, you get the value of y at the tip and dy dx at the tip. Now, x equals to L means this goes off. So, you have 5 L to the power 4 L to the power 5 minus L to the power 5 4. So, this becomes q0 by 30 q0 L4 by 30 EI. That is the value of the deflection, which is again negative, shows downwards, and at x equals to L, if you compute this, you get minus q0 L cube by 24 EI as the slope of this particular pre-n. Well, then to summarize, in this particular lesson we have seen the evaluation of slope and deflection of non-prismatic beams using moment area method, and also we have looked into the examples to evaluate slope and deflection of different types of beams for different loadings. Now, this is the last lesson of this particular module, and in this module, as we have seen, it includes 4 lessons. In the first lesson we have discussed about the derivation of differential equation of elastic curve and its application. Then subsequently we have introduced the concept of superposition method in the lesson 2. In the third lesson we have discussed about the concept of the moment area method, the moment area theorems and its application in evaluation of slope and deflection, and in this particular lesson today we have seen the application of moment area theorem in non-prismatic beams or beams with the variable moment of inertia. Now, these are the questions set for you, that what will be the value of deflection in a simply supported beam if the moment of inertia is double, what will be the value of end slopes in a simply supported beam if the span is double, and what is the value of slope at the tip of a cantilever beam subjected to concentrated load P at the tip of the beam. Now, answers for these will be given to you in the next lesson. Thank you.